Pause the video if you need to read the question. I highly recommend that. So we're told at the beginning that k is less than 3. That just says that the km mass is the smaller of the two masses, or the lighter of them. So that's going to accelerate up, and q is going to accelerate down. It's the heavier one. Fine. Everything else that you read in this paragraph is what you'd normally expect. A light, inextensible string. So just to remind you that light string means we ignore the mass of the string. Inextensible string means that the two accelerations of P and Q are both of the same magnitude. And the smooth pulley means that the tension is the same in both parts of the string. We're actually asked to explain that in part C. The system's held at rest, so to begin with, these particles are stationary. That's not always true, but it normally is. And they are next to each other at the same height. The system's released from rest, zero velocity, as we've said. And then we're actually given the acceleration. So normally we're not given the acceleration. We have to work out T in tension in the string and the acceleration. Here we're given the acceleration, but in a moment we're actually going to be asked to work out K using that. It's exactly the same drill as normal. We need to set up force diagrams, a separate one for each of the two particles. And those might look like that. I've squeezed that into the corner of the page because there's a lot to do here. So just be comfortable that whilst there are separate force diagrams, they're tied together through this tension, which is the same T, because it's a smooth pulley. And once you've drawn the force diagrams, it's sensible to do F equals ma for each of the separate force diagrams to get two equations, which should allow us to solve some simultaneous equations. But I would add one more thing to these diagrams, and that's just to identify the direction of the acceleration. And we'd normally do that with a double-headed arrow. We know P is going to go up or accelerate upwards, and Q is going to accelerate downwards. And since we know that acceleration, which is here, I'm going to add that to the diagram as well. So I'm going to put G over 3, which is a third G. Great, and we can use those as our positive directions for each of the F equals ma applications. Right, let's get on with that then. F equals ma. Remembering that F is the resultant force. So for the first diagram, for P, T is a positive force minus kmg, because that's pointing the other way. M isn't m, it's km, remember. It's the mass is km, not kmg, just km, because it's a mass here, not a weight. A we know, which is a third g, or g over 3. Okay, let's do F equals ma for the second, for Q. This time I'm pointing down is my positive direction, so I'll have 3 mg. T is pulling the other way, equals 3m, which is our m, which is our mass, times a again, which is g over 3. Now that cancels actually, doesn't it? 3m times g over 3. These 3's actually cancel there. So I'm just going to actually in situ, obviously you wouldn't do this in the exam, you wouldn't rub things out and replace them. You'd write it on the line below, but just to save space here, I'm going to replace that with just mg. And again, just to simplify what's on the screen, I'm going to remove F equals ma and just have those two simultaneous equations next to each other like that. Because this point here should be familiar when you're solving mechanics force questions with connected objects. To combine these two equations together, regardless of what you're asked to do here, is a good idea just to add the two equations together. Because you've got a positive t here and a negative t here. A really good way of just eliminating that is just to add the two equations together. If we do that, we get 3mg minus kmg equals the sum of these two, which is kmg over 3 plus mg. Okay. We can do some cancelling now because there's an mg in every one of those 4 terms. So we've got, oops, sorry, we've got M's cancel and the G's cancel. I'll replace that with a 1, so it's a third, and that becomes 1 as well. So let's tidy that up and see what we've got. We've got 3 take away K equals, that's K over 3, or a third K, plus 1. And if we rearrange that, we can find the value of K. Well, if I add K to both sides and subtract this 1, then we'll get 2 equals 4/3 K. And that very quickly tells us that K is equal to, well, times by 3, divide by 4, 6 over 4, which is 3 over 2, which is 1.5 as required. And we realize actually we've solved part B before we've solved part A. That's fine. In the exam, you'll get the credit for that, even if you've written it in the part of the paper that's, that's defined for answering part A. You'll get that credit. It'd be a good idea to state it again in the section for part B and just say, I did the working for this in part A. You will get the credit for that. So we've done part B, actually, which is kind of this section here. Let's go back and solve part A now, because now that we know K, we can substitute that back in and find the tension in the string. We're going to need to use the first of these 2 equations because the other one doesn't even have a K in it. So let's substitute that in. So substituting K into that equation gives this. I'll just say that I've substituted K equals 1.5 into that. And that gives us this equation here. Let's simplify that. That term there, 1.5 times a third, isn't it? We've got a 1.5 divided by 3 there. So really that's just a 0.5. So again, I'm going to change that in situ. So let's change that to a 0.5, and of course the G over 3 is just now just a G. And then we can add 1.5 mg to both sides of the equation. We get T equals 2 mg, and that would be in newtons. So that's our answer to part A, isn't it? So we can say that this is our answer to part A. Don't worry about the fact that it's got an M and a G in it. G is a known quantity, it's 9.8. If you want, you can write this as 19.6 m newtons. That's just 2 times 9.8. It's 19.6. But we can't get rid of the m. The m is just intrinsic to this question, and it makes sense, doesn't it? We just think about this. This is saying that T is dependent on M and G. So if we increase M, well, you'd expect the tension to increase, wouldn't you, with greater masses? So no surprise there. And similarly, if you increased G, for example, if you did this experiment on a planet, a bigger planet with a greater gravitational constant at the surface, then you'd expect the tension also to increase. So no surprise that that's dependent on both of those quantities. Let's just have a quick look at C before we go on and do the main parts of the question. Tough bit, I think, which is the SUVAT section, which is part D. C just asks us how we've used the information that the pulley is smooth. And that's simply that the tension in the string is equal on both sides of the pulley. If you want to have an intuitive understanding of that, imagine a really rusty, rubbishy pulley that hasn't been used for a long time. If you hang a string over it and that string's kind of locked onto the pulley, imagine it's, just imagine a stiff pulley with lots of friction in it. And imagine you pull hard down on here. You hang on to it, you pull with all of your own weight down on there. And imagine the pulley sort of creaks around a little bit. Well, there's going to be huge tension in this side because you're pulling really hard on that, trying to get the pulley itself to rotate. But hardly any of that kind of force is going to translate onto the other side. The other mass is barely going to accelerate up at all, because a lot of what you're doing, a lot of the actual kind of weight that you're pulling, the force that you're pulling down on that right hand string with, is just getting kind of lost in the friction in the pulley. So in that case, you would have a different tensions in the strings. Smooth pulley means the same tension on both sides. Right, D. Again, pause the video if you need to have a good read of this question. But to demonstrate this, let's have a little look at this demonstration here. So let's just play this and see what happens. happens. Watch carefully. Did you see that? I'll run it again. This block, watch it. So just playing that in slow motion, when this block hits the ground, it stops instantly. That's the model that we're using. It just stops. But the other one doesn't, does it? This one stops. The string then goes slack because it's just kind of been crumpled into itself. But this block has got some vertical velocity at that point. There's nothing to stop it instantly. So it's going to carry on up just a little bit and fall under gravity. Eventually it'll hit the kind of length of the string again and stop. Or it will undergo motion then that's a bit complicated. So we don't look at that in A level. But let's just run that one more time. We're going to make the mass a little bit bigger for the B mass, so that it accelerates a bit harder. And again, watch what happens to the smaller mass. Well, that time it was projected a lot higher into the air and it almost hit the pulley. So we've got to, in this question, we've got to show that the greatest height reached by P is this value here. So that's going to, there's sort of two parts to that, arguably even three. There's its initial height, we need to work out what that is. And that's just the distance that B is, Q, in this case, is going to fall. So that'll go down that much and P will go up that much. So we need to work out what that is. And then we need to get this extra bit here. How high does it go before it falls back down and hits the string again? Okay, let's do it. So firstly, we need to find the distance that Q falls. Well, let's see what information we've got. We want to know S. It's released from rest. We're not, well, we will be interested in V, but not right now. A, we know is G over 3, because that was told to us here in the question. And we've used it before, so G over 3, or a third G. Sorry, I've written that in the wrong place. G over 3. And the time we're told in the question also is 1.8 seconds. Okay, well, we can use S equals UT plus a half AT squared. Because since U is 0, we can kind of ignore this term here. And we'll get S equals half times G over 3, remembering that G is known, times 1.8 squared. Keeping everything in terms of G, I'm going to write that down. If we calculate that using calculator, we get 0.54 G meters. Okay, if you want, you can write it as, times it by 9.8 and find out what that value is. But that's fine what we've got there. Now, remembering that that's just the distance that this block has fallen, so Q must start, so P must start at that height and then go up that same height up to here. So we're going to need to double that value later to find out what this height is. Now we need to look at this extra bit of motion, which is the free fall part under gravity. Well, in order to explore that, we're going to need to know how fast P was moving at the point where Q hit the ground, because otherwise we're not going to be able to explore that extra bit of motion. Well, that's just the same suva. We just need to work out what this V is here. So let's try and find that too. Well, for that, we can just probably just use V equals U plus AT. Again, the U is 0, so it's quite easy. We get V equals A, which again is G over 3, times T, which is 1.8, which is just going to be 0.6 G meters per second. So just to keep track of things, let's underline some of our key pieces of information that we've got here. Right. Okay, I've just added, just to say that we've also added, I found the velocity of P when Q hits the floor, which is the same as the velocity of Q hitting the floor. Okay, so now we need to look at the second phase of suva here, which is the free fall. Now remember, free fall, we always think of things moving down when they're falling, but free fall just means that something's moving purely under the action of its weight or gravity. And that could be going up or across at the same time. It could be having some sort of trajectory like this. As long as the only force acting on an object is its weight, it's in free fall. And of course, P is going to be in free fall as soon as the string goes slack, even though it's moving up to begin with. So let's see what we know about that. We know it's this constant acceleration, but this time A is just going to be negative G. Because the only force acting on that object is its weight. What else do we know? Well, we want to know S, because that will give us information about how high it is. U, the start of this motion, is the V from the end of the previous phase of motion. So we can put that in as 0.6 G, and it's positive because it's moving up. V, well, this is for us to decide. V, we're interested in the greatest height of the object. And of course, that is when it's got 0 velocity, which is there. So that greatest height is there, when it just stops just for an instant. Okay, so we have V is 0. And this time T we're not interested in at all. Now we can tie all of that together using V squared equals U squared plus 2AS. This time V is 0. So we can say 0 equals 0.6 G squared plus 2AS, and that's going to be minus 2GS. Now, it might look like an awkward equation to solve that, but it's not really. We expand the bracket, we've got 0.36 G squared minus 2GS. We can now divide both sides by G. A better way to do that really is to factor out the G and then realize that we don't need to worry about that. So minus 2S. We've got a 0 product here, so either G is 0, but it isn't obviously because G is 9.8, or this bracket here is 0. It's equivalent to just dividing by G. Rearrange that, so that's 2S, and it looks like 25. 2S equals 0.36 G, so 1S equals 0.18 G, and that's also in meters. And then we're basically done. We just need to remember that we need to do twice this height plus this height, and if you do that, you get the answer that we need. Total height equals 2 lots of 0.54 G plus 0.18 G, and that is 1.26 G meters as required.